Yeah, good afternoon, all the students. I just gave you some time to relax because you have attempted your exam, right? Mini project. Okay, we'll start now. Can you see this presentation? Yeah, now let's move on to this fourth lecture under module 2. Fourth or fifth we have to start. 1 second. Yeah, fifth lecture under module 2. In today's class, we are going to see about what is inductive bias in detail in decision tree learning and how the learning systems or learning methods make a decision between or make a selection between restriction biases and preference biases, and why we tend to prefer short hypotheses. Okay, so when we are making some assumptions in any type of learning, let it be finders algorithm or candidate elimination algorithm or a decision tree algorithm, when a learner is learning according to a particular algorithm, what assumptions does it make? What inductive bias will it have in order to generalize well to the unseen data? And we understood from the previous chapter that finders algorithm and candidate elimination algorithm, they both have the inductive bias or assumption as only conjunctive combinations of attributes are allowed. Disjunctive combination of attributes, if considered, it will lead to infinite hypothesis space, means lots of solutions will be available. Now, when a new unseen data is given to the learner or the machine learning algorithm, it may not be able to generalize well. It may predict wrongly because it will consider every possible alternative. Instead of that, if there is an inductive bias that only conjunctive combination of attributes are allowed, disjunctive combination is not allowed, means only strict rules are allowed, and this also should be true and this also should be true, like that. If you have, then there will be limitation on the hypothesis, right? So that it can easily generalize well and predict well with unseen data also. When some new data point is given, it will be able to predict about that properly. Means its generalization capacity will increase by making some assumptions. So it is not wrong to make some assumptions while learning or have an inductive bias while learning about the training examples. Okay, now in today's class, along with the inductive bias, what we have learned in the previous session, that is shorter trees are considered over longer trees or complex trees, and the statistical measure that is used in order to select the shorter trees is information gain. These two are the assumptions as we have learned in the previous session, right, for decision tree algorithm. Now, under that, let us further see what is restriction bias and what is preference bias. Now, what is the policy by which ID3 generalizes? Generalizes means what? What is the meaning of generalization? Predict something correctly. Okay, so these terms will be used frequently hereafter. So you should not have any doubt about those small terms that are being used while explanation. You should be very clear about those terms, right? What is the policy by which ID3 generalizes? Means what is the inductive bias it follows? What is the assumption it makes? Okay, that is that has to be understood. Generalizes means it should be able to predict correctly when some unseen data is given. The machine learning algorithm will learn from the training examples, the behavior of the data it tries to understand, and it will try to generalize or predict correctly when some new data point is given, when some unseen data point is given, right? That is called as generalization capability of that learning algorithm. Now, given a collection of training examples, there are typically many decision trees consistent with these examples, right? Now, when I give this 14 data points example again to you, not only one decision tree, but actually you can construct lots of decision trees, right? Say you just omit outlook. Okay, that attribute you try to omit. Then you can construct different set of decision tree, right? Different shape of the decision tree. And like that, without considering information gain as the deciding factor in order to generate the split point, if you take all the attributes as each as root node once, then you will be able to generate some 4 decision trees. Again, under those 4 decision trees, you will have lots of combination for the remaining 3 attributes, right? Say taking taking outlook as the root node, you have one decision tree. Having sky, say climate, what is observed on the day, say rainy. Rainy, if you take as the root node, you may have another decision tree. Now you take outlook on the first root node and humidity on the next root node, or rain on the next root node, or humidity on the next root node, whatever different attributes you take on the next root node, you will come up with different types of decision trees, right? So each combination, there are total 4 attributes, means you will get 2 power 4 combinations, correct? Now those many decision trees can be built for the training set given. Now, given a collection of training examples, there are typically many decision trees. That is what I'm trying to tell. Many decision trees consistent with these examples, right? It can cover all the training examples. Different kinds of decision trees you can build in order to cover all the training examples. Now, what is the question? Which of these decision trees does ID3 choose? Which of these possible decision trees does this ID3 algorithm choose? What we are doing here is we have lots of solutions. All are correct. Now, which one to choose? That is the problem. Which of these decision trees should be chosen by ID3 algorithm? What is the strategy that is followed by ID3 search? What is the plan? What are the factors that are considered by this ID3 algorithm? It selects in favor of shorter trees over longer ones. This is one of the strategies. It will try to select simplest, shortest trees which have lesser levels. Means, say if you take a tree like this is a tree having 1 level. If you take further expansion of this tree, it is having 2 levels, right? So when this ID3 starts searching for its best decision tree, how it makes its selection? In favor of shorter trees, simpler trees over longer or complex trees. And what is its second strategy? Selects trees that place the attributes with highest information gain closest to the root. Correct? That is the essence or the flavor of this decision tree algorithm. Without this, we come up with lots of decision trees. Without the second strategy, ID3 algorithm will find lots of decision trees suitable for the training examples, but all decision trees can be considered, right? Each time when a new data point is given, does the machine learning model search all these decision trees possible in the hypothesis space? No, that is very time-taking task, and it will make that machine learning model less efficient. That is why it has another criteria in searching the hypothesis space. That second criteria is selects trees that place the attributes with highest information gain closest to the root. The root node is selected by attribute having highest information gain. Correct? That will provide the best classification, so that the tree further constructed will be simpler. It will not get complex. Say, if at all you select temperature as the root node, what will happen? Temperature is the attribute which is giving less information gain. lowest information gain, right? Now, if you keep that as the split point in the root node, what will happen? You have to check every possible alternative combinations with that particular temperature. So you keep on extending the tree so that it reaches to 3-4 levels. Means you are making the tree complex, right? But what is the preference of ID3 algorithm? It tries to select only shorter trees. So how to have an inclination towards that shorter trees? How do you bend towards that shorter trees? By selecting the information gain as the statistical measure, as the mathematical measure in order to construct the decision tree. The attribute having the highest information gain, if placed at the root node, it will give better classification and result in lesser complex decision trees. Okay, so these are the two strategies that are followed by ID3 algorithm in order to keep its decision tree, optimal decision tree, as simple as possible. Okay, now the approximate inductive bias of ID3 is, we have seen this in yesterday's class, right? Shorter trees are preferred over larger trees. Now, ID3 can be viewed as an efficient approximation to breadth first search ID3. This I have explained you in yesterday's class. Breadth first search means first it will search for all shorter trees, then goes for next level trees, then goes for next level trees. It is searching breadth wise. That is why ID3 algorithm can also be called as breadth first search ID3 algorithm. It uses a greedy heuristic search. It searches every possible alternative. That is why it is called as greedy heuristic search, to attempt to find the shortest tree without conducting the entire breadth first search through the hypothesis space. Now it has to minimize its search, right? In order to minimize its search, what it does, it keeps on checking all the shortest trees first. If there is a match found, yes, optimal decision tree is found. It stops its search there. It will try to minimize its search from the hypothesis space of possible decision trees. Now, what is the search strategy? Finding shorter trees compared to the larger trees. Now, because ID3 uses the information gain heuristic, heuristic is nothing but it's a random measure. Okay, information gain heuristic and a hill climbing strategy. I told you what is this hill climbing strategy, right? When you are climbing a hill, you will take for the local optimal direction. You see in all directions, wherever the inclination of the mountain is high, you tend to go in that direction, right? So you're making a locally optimal decision. In the same way, even the decision tree makes a locally optimal decision at each node by calculating the information gain. If the information gain is high for a particular attribute, that is taken as the split point. Got it? Now, a closer approximation to the inductive bias of ID3 now. Now we are trying to refine it better. How about what is the inductive bias that ID3 algorithm has? What is the assumption that ID3 algorithm makes? Okay, shorter trees are preferred over longer trees, and trees that place high information gain attributes close to the root are preferred over those that do not. Okay, these are the two strategies or assumptions that are made by decision tree algorithm like ID3. Now, the important concept, restriction biases and preference biases. Let us understand with respect to these two algorithms, ID3 and candidate elimination algorithm, what is restriction bias and preference bias. Try to understand the meaning first. Restriction bias means it's having some restriction on the biases. It has some restriction in selecting the assumptions. Preference bias means you can prefer it. You don't have any restriction. You can make a choice in the bias, right? Now let us proceed and see what exactly they are. Consider the difference between the hypothesis space search in ID3 and candidate elimination algorithm. In candidate elimination algorithm, the hypothesis space, we also call it as version space. You remember, version space is represented as VS with all possible hypotheses that are consistent with the training examples D, right? That is called, here I'm writing VS. Version space is set of all possible hypotheses with inconsistency with the training examples D, right? That is the version space. Then what is the hypothesis space in ID3? It contains all the optimal decision trees that are built by learning from the training examples, right? Now ID3 searches, see this explanation what I have underlined, it is very somewhat beautiful to understand. Why? Because they are just interchangeable. As I go on explaining, you'll understand. ID3 searches a complete hypothesis space. It searches complete hypothesis space of the decision trees, and it searches incompletely through this space. Understand carefully. It searches the complete hypothesis space, but incompletely searches through this space. Means the hypothesis space is complete. It contains all possible solutions for the problem at hand. It has all possible hypotheses in consistent with the training examples, right? That is why we call it as complete hypothesis space. Now, ID3 algorithm searches it incompletely through this space. Why we call it as incomplete search through this space? Because it doesn't search each and every decision tree. It takes the information gain measure, finds the best attribute, and goes to the next node, finds the information gain for remaining attributes, finds the best attribute, takes it as split point, and proceeds further. And that is its optimal decision tree. It doesn't keep on searching every possible decision tree. That is why we call it as incomplete search through the space. Though the hypothesis space is complete, it searches the hypothesis space incompletely. Though the hypothesis space contains every possible solution for the training example set, it searches that space incompletely by just considering the information gain measure, right? It searches incompletely through this space from simple to complex hypothesis, right? It starts with a root node, grows the tree, again generates the split points based on information gain, further constructs the tree. It goes on by making the tree complex, right? From simple to complex hypothesis, it moves until its termination condition is met. Means until it finds a hypothesis consistent with the data. Once the decision tree consistent with the data is built, that is the termination condition, and there the construction of decision tree will be stopped. Understood clearly? Now I am reading it once again. It is very nice to read. ID3 searches a complete hypothesis space, but it searches incompletely through this space. You understood now? Now let's go to the next point. In candidate elimination algorithm, how this searching happens. Let's see. The version space candidate elimination algorithm searches an incomplete hypothesis space. See, here it is complete hypothesis space, but in candidate elimination algorithm, it searches through incomplete hypothesis space. That is one that can express only a subset of the potentially teachable hypothesis or potentially teachable concepts, right? So the hypothesis space is incomplete. It may not sometimes contain the optimal hypothesis that will be consistent with the training examples also. That is the risk in candidate elimination algorithm, right? So the version space of candidate elimination algorithm searches an incomplete hypothesis space which may not contain the target value, which may not contain the target function, or which may not contain the target solution, but it searches this space completely. Again, interchange, right? It searches the space completely. Candidate elimination algorithm's version space is incomplete hypothesis space, but The candidate elimination algorithm searches that space completely. It searches each and every hypothesis. It tries to find whether each and every hypothesis is consistent with the training examples. If any hypothesis is found to be not consistent, that hypothesis is eliminated from the hypothesis space. That is why it is called as candidate elimination algorithm. Got it now? Now let me read once again. ID3 searches a complete hypothesis space. It contains all possible solutions and it searches incompletely through this space by considering only simple decision trees. Now come to the other part. The version space of candidate elimination algorithm searches an incomplete hypothesis space. It may not contain the target function, but it searches through the hypothesis space completely, so that it will eliminate any hypothesis that is found to be inconsistent with the training examples, right? That is what is called as restriction and preference bias. We are entering into that area now, okay? Let me make it more clear to you. Now, the inductive bias of ID3 follows from its search strategy, whereas the inductive bias of the candidate elimination algorithm follows from the definition of its search space. Okay, so the inductive bias of ID3 lies in the search strategy, lies in its search plan, how it searches the hypothesis space. Okay, but candidate elimination algorithm's inductive bias lies in its search space itself. The set of hypotheses that lie in that search space itself. Remember, version space will try to minimize the hypothesis space so that it contains only hypotheses that are consistent with the training examples, right? So this candidate elimination algorithm the inductive bias of this candidate elimination algorithm is in the definition of search space itself. Okay, now I am repeating again. Inductive bias of ID3 follows from its search strategy, how it searches through the hypothesis space to select the optimal decision tree, whereas the inductive bias of candidate elimination algorithm is from the definition of its search space itself. It tries to minimize the search space so that it finds the optimal hypothesis, or it contains only the set of hypotheses that are consistent with the training examples. Okay, now the inductive bias of ID3 is just a preference for certain hypotheses over others, for shorter hypotheses mainly. So what are the assumptions in this ID3 algorithm? It prefers some hypothesis over other hypotheses, shorter decision trees over longer decision trees, simpler decision trees over complex decision trees. That is how you need to understand about the inductive bias of ID3, right? What it is doing here, it has lots of optimal solutions. It has lots of options, but it is preferring only one optimal decision tree by considering the measure called as information gain. That is why we call it as the preference bias. Understood clearly now? The inductive bias of ID3 is thus a preference for certain hypotheses over others, means preference for simpler trees over complex trees. That is why we call it as preference bias, or alternatively we can also call it as search bias. It is restricting, it is biasing on its search, it is limiting its search so that it prefers only simpler decision trees rather than complex decision trees. Got it? Now, in contrast, let us see the other algorithm. The bias of the candidate elimination algorithm is in the form of a categorical restriction on the set of hypotheses considered. There is restriction on the hypothesis being considered. If the hypothesis is not consistent with the training examples, remove it. It is not fit to be in the hypothesis space. This form of bias is typically called as restriction bias, or simply we can call it as language bias. Why we call it as restriction bias? You're restricting, putting a restriction on the hypothesis that if it is consistent with the example, training examples, keep it in the version space. If it is not consistent with the training examples, eliminate it from the version space. That is called as restriction bias. So the inductive bias in candidate elimination algorithm is restriction bias, and the type of inductive bias in ID3 algorithm is preference bias. Clearly understood now? Now, which type of inductive bias shall we prefer? Or which type of inductive bias shall we ask the machine learning model to prefer? A preference bias or a restriction bias? Which one? Let's see. A preference bias is more desirable than a restriction bias. Note, a question may be answered on this topic. Okay, asking your view about restriction bias and preference bias, and which one do you select if at all you are given with this kind of problem definition. Okay, so keep an eye on this, focus and understand clearly. A preference bias is more desirable than a restriction bias. Why? Because it allows the learner to work within a complete hypothesis space that is assured to contain the unknown target function. When I say complete hypothesis, space, it contains all the possible solutions along with the target function also, ideal target function also, right? Then it is always better to search the entire hypothesis space, though your search strategy is partial. Understand clearly. You're searching the entire hypothesis space, but your search is partial. Your search is partial and is bending towards shorter trees. How shorter trees are built? By calculating the information gain and building the optimal decision trees by taking the best split point, right? So in ID3 algorithm, it searches the complete hypothesis space, but partially. It searches partially by considering the statistical measure information gain. It is prefer shorter trees over longer trees. That is why it is always better to prefer, it is always better to choose preference bias, because there is no risk of omitting the ideal target function. Ideal target function will always be there in the hypothesis space because the hypothesis space is complete. Okay. Now, in contrast, what does a restriction bias do? A restriction bias that strictly limits the set of potential hypotheses is generally less desirable. We don't want that. We try to overcome that kind of biases, restriction biases. Why? Because it introduces the possibility of excluding the unknown target function altogether. Sometimes there is risk of eliminating the unknown target function without knowing. And remember, the hypothesis space is incomplete, though you search completely, right? So you have to be very careful while using this restriction bias. That is why decision trees perform better when compared to candidate elimination algorithm or for this one, finders algorithm, right? But some learning systems combine both of them. As you go on with advanced machine learning models, they combine both of these biases. They may have restriction biases as well as preference biases also, based on the context. Okay, that will be covering in later chapters once you understand the core concepts. Now, why prefer short hypothesis? Why not long hypothesis? Why not complex hypothesis? Why not lengthy hypothesis? Why to prefer short hypothesis? See, when you take some physicists or people making study on astrophysics or some other kind of science, They formulate their hypothesis as simple as possible, though more complex terms are available. See, an equation E is equal to mc square, or you have a equation for gravity. All these equations are given in a very simple format, though there is complex, concept lying behind, right? Why do they prefer this short kind of hypothesis? Say, there are some 1,000 hypotheses which will fit to the training examples, or which will fit to the observed data. Now, among them, some hypotheses may not be able to generalize well, means they may not be able to predict or apply properly in new circumstances. But if you take some 100 short hypotheses, when compared to 1,000 long hypotheses, if you take some 100 short hypotheses, and all these are fitting very well with the training examples, now there is less likely chance of coincidence that short hypotheses fit the problem. Why I'm telling this is, when there are less solutions and they are optimal solutions, coincidence may not be existing. Means by chance you didn't select these solutions, they are optimal solutions. But whereas you consider 1,000 long solutions, there may be some coincidence with their matching to the problem. Got it? That is why scientists tend to select the short hypothesis when compared to long hypothesis. Okay, is ID3's inductive bias favoring shorter decision trees a sound basis? Does it have a sound support in the history for generalizing beyond the training data? Is there any good support for this kind of assumption? ID3 makes an assumption that it prefers shorter decision trees over longer or complex decision trees because they may generalize well to the unseen data. But does this assumption have any support historically? This is most debated question among the scientists from nearly 1300 century. See this, that is formulated, recorded by Occam's razor, and he made a statement like this: prefer the simplest hypothesis that fits the data. Prefer simplest hypothesis that fits the data. This is also called as minimum length principle. When there are more alternative solutions, more number of alternative solutions available, always find the simplest of the solutions. This is called as Occam's razor method, and it is widely being used in many departments in current days organizations. When there are lots of solutions available, always prefer the simplest solution. Okay, that is called as Occam's razor. Prefer the simplest hypothesis that fits the data. As I told you, the chances of coincidence will be less likely in less number of suitable hypotheses than in more number of long suitable hypotheses. Less number of short suitable hypotheses will have less chance of coincidence in matching with the problem area than large number of long hypotheses. Okay, that is explained by this Occam's razor theorem. Now, let me introduce you what are the issues in decision tree learning which can be elaborated in your next class, right? So the issues in decision tree learning are avoiding overfitting of the data. Overfitting of the data means the avoiding the machine from learning too much so that it can't generalize with the unseen examples. Means if the machine is learning too much from the data, it can't generalize well from the it can't generalize well on unseen data or new data points. That is called as overfitting, right? It is learning all possible hypotheses. It is learning every possible hypothesis in the hypothesis space, which makes it less generalizable for the unseen data. Okay, generalization capability means by assuming less number of attributes, it should be able to generalize more. It should be able to be consistent with more training examples. It should generalize well on unseen data by considering less number of hypotheses, not more number of hypotheses. Okay, so if the hypothesis space is having lots of hypotheses which will hold for all the training examples, they may not generalize well to the unseen data. This is called as overfitting. Now, decision trees tend to overfit with the training examples. Now, how to avoid that? And incorporating continuous values attributes with the decision tree learning, alternative measures for selecting the attributes, handling training examples with missing attribute values, and handling attributes with different costs. Okay, all these issues we are going to cover in next session in detail. Now quickly tell me what is overfitting in one simple sentence. Students, you are there? What is overfitting? Learning too much or learning very less?
Learning too much.
Learning too much. Machine learning model learning too much is called as overfitting. Now underfitting means machine learning model learning very less. It is not covering all the training examples. That is called as underfitting. Now what is a split point? What is split point in the decision tree? What is a split point in the decision tree? Say if you calculate the information gain for all the attributes in the training examples and you found that Outlook has more information gained, that you place at the root node. So Outlook is called as the split point, right? Now you proceed further. Now information gain of humidity is high. So humidity is called as the split point. Why? Because it is allowing us to split the data or the training examples according to some conditions, right? So, that is why the nodes in the tree are called as split points. What is inductive bias in decision tree learning? You have to answer this. This point is being discussed from last 3 classes. What is inductive bias in decision tree learning? There are 2 assumptions, right, with respect to decision tree learning. What are those assumptions? Any one of you? What are the assumptions in decision tree learning? Umehani? Yes. Tanuj? Who is that? Who tried to answer?
Generalize a finite set of observations.
Be louder.
To generalize a set of observations, ma'am.
The voice is breaking.
Selects in favor of shorter trees over longer ones.
Selecting shorter trees over longer ones. What is the second assumption?
Selects the trees that place the attribute with highest information.
Very good. Urugesh, right?
Yes, ma'am. Yes,
Okay. Highest information gain. Selecting the trees which places the attribute at the root nodes having higher information gain. Okay, these 2 are the assumptions. What is Occam's razor? In simplest terms, as you understood it. You need not present the theorem as it is. Just tell me what is Occam's razor? What does it prefer?
simplest hypothesis that fits the data.
Simplest?
Hypothesis that fits the data.
Very good. Simplest hypothesis that fits the data has to be considered over long hypothesis. This is also called as minimum description, minimum description principle. Okay. Yeah, that we'll see in further chapters. Any doubt till here, students? With next
No,
session,
ma'am.
we'll be completing this chapter and start with artificial neural networks. So don't keep any doubts in your mind. You can also ask me over WhatsApp if you have any doubts while studying. Right? We'll meet in the next class.